Hello students, Jai Hind to all. So students, we are going to start today discussion on the uh, network protocols. So there are so many network protocols are there. So in this chapter computer network part 2, today we'll discuss about the TCP packet format. That is the network layer. At the network layer, two protocols runs TCP and IP. So this already we have discussed in the previous classes. So now see that how what information this protocols, what rules this protocols contains in the packet format, how it looks like. So so see on this students, this is a fundamental protocols means set of rules that how the communication will be established between the two devices over a network. So this packet format this works on the third layer, that is called the network layer, layer of the OSI system, that is the open system interconnection. So in the this OSI, as you know, this is of 7 layers, and that third layer is the network layer. So at that layer, the packets are sent from one computer to the other computer in the form of packets, or one router to the other router in the form of packets. So this will see. So it offers dependable and organized data distribution between the applications that are executed on several hosts in a network. So understand. So this TCP what does? It organizes the data distribution, how the data will be distributed between the applications which are executing on the computers in several hosts in a network, which is a part of a network. So students, this packet format must be understood in order to analyze and resolve network communication issues. So if suppose while sending a packet, if any packet is lost, if packet doesn't reach to the destination, and then how this issue will be resolved. If suppose any error happens while sending the packet, then how this issue will be resolved. Who will check the whether packet is what we have sent is not tampered. So these all issues are resolved at this layer. So the TCP packet format we'll see here. Now see this TCP packet, see this is a 32-bit. So this packet format is of 32-bit. So this you are seeing the source port address and the destination port address. This contains the source port address, which port it will deliver, and destination port address, at what port it will be delivered. So there are so many ports windows in the computers through which the data enters to a device and leaves the device. Next is the sequence number given to the each packet. So previously, which we have discussed, that this TCP divides the data into a small packets, because every network devices, every computers has a capacity that how much data it can receive at one time, how much data it can send through the channels at one time. So due to that, the big size data we have to divide into small packets, small chunks, so that it can be easily sent over a network from one router to the other router, from one network device to the other network device. Now, if suppose a big file is divided into 100 packets, so each packet, this TCP will assign a number that is called a sequence number, packet number 1, packet number 2, packet number 3. Now, at the receiver and students, the receiver will accept the packets in the form of this number. If suppose the receiver is expecting about the packet number 3, but it got the packet number 4, packet number 4, so it will not receive the packet number 4 until and unless it will not get the packet number 3. So what it will send the so it will wait for the packet number 3 first. Okay. Now acknowledgement number. After receiving any packet, the receiver will send the acknowledgement number that I have received this packet number 3. So by getting this acknowledgement number, means who? Sender will send the next packet. Okay. If suppose the sender will not get the acknowledgement number of any packet, so it will retransmit the packet again by assuming that the packet is lost between the network. Okay. So here are some data offset bits are there. So this acknowledgement number is also 32-bit number, sequence number is also 32-bit number. So you can understand that how many packets it can be divided. So 2 to the power 32 packets in this number of packets big data can be divided. Similarly, the acknowledgement number also can be given the same size. So here some bits are there, data offset bit, reserve bit, flags, Windows sliding protocol, that how the Windows means one window means what size of the packet. After sending the data, it will slides or move. Checksum for checking the errors. So if the data what is received is in the proper condition or not. Now some urgent pointer means this packet is to be delivered as soon as possible. For these urgent pointers are there, some options, some padding. Now here the data payloads are added. Now we'll see this about. So see, this TCP packet has three fields. As these fields: source port, which is of 16 bits. It holds the source transmitting application's port number, and it helps in determining the application where the data delivery is planned. Like the HTTP hypertext transfer protocol, students work on port number, use port number 80. Destination port 16 bits. This field has the port number of the transmitting applications and helps to send the data to the appropriate applications. Next, the sequence number 32 bits, which I have discussed, that it ensures that the data is received in proper order by order segmenting, and it also do the reassembling task, reassemble them at the receiving end. Acknowledgement number 32 bits, this field contains the upcoming sequence number and it acknowledges the feedback up to that. Data offset, this is a 4-bit, which I have shown you, that is a 4-bit. The data offset field indicates that the starting point of the TCP data payload. Also, so this is, it talks about that the starting point of the TCP data payload also stores the size of the TCP header. That what is the size of the header, how much byte it is. So basically the TCP size is 20 byte to 60 byte. And control flag, this is 9 bits. This uses a few control flags to regulate the communication. Some of the flags include what? Sync, synchronization. So this code is given, responsible for connecting the sender and receiver, means there is a synchronizations in the data. There is no delay. Acknowledgement, its purpose is to transfer the acknowledgement of whether the sender has received the data or not. That is the acknowledgement here. This is used in the control. ACK bits. Finish, it informs whether TCP connection is terminated or not. Finish means if the data transfer is over, so it will make this bit high. That is the finish. RST means reset, mainly used to reset the connection when an error occurs. Suppose any error occurs, so RST bit will send to establish the connection again. Window size, see, this is of 16 bits. The size of the sender receive window is specified by this property, that what is the size of the window. In that size, the TCP will divide the data into packets, into the packets of that size. Checksum, it reveals if the header was damaged during the transportation or for error. Urgent pointer field, this is also 16 bits. This field points to the packet's first byte of urgent data. So this packet you deliver to the destination as soon as possible, means on the priority basis, and others packet will be kept on the hold. So this will represent the different TCP options, variable length. Data payload means how much data you are sending, this packet is carrying. So this field may contains information which is the actual application data that is being transmitted. So that in the terms of which checking the data size. So next, students, about this IP packet, that's the internet protocol. So what is the structure of this? The IP packet, this is used for the data transmission in the computer networks, and this data units received from the layer above are encapsulated in an IP packet. Above layer is the data link layer. So the frame which is coming to this network layer, the IP layer, put its header, and after that it convert into the packet and pass to the next layer, transport layer. And additional header data is added. IP payload is the term used to describe the enclosed data. All the information required to deliver the packet at the other end is in the IP header. Now this is the envelope, this is the IP packet. Now see what is the structure. Version, which type of the IP version, two types of the IP packets are there. IP version 4, which is of 32 bit, and IP version 6, which is of 128 bits. So this version will tell that a number 32 bits. So here it will be the decimal code of the 32. So this is a type of service. Which type of service it is? Total length of the header, it will be represented by the 16 bit. Here the identification, flag bit, fragmentation offset, time to live for what time over the network this packet will live. So suppose this time is over, that is around 8 bit. So if that much time is passed over a network, it doesn't reach to the destination. So packet will itself will be destroyed over the network. Now the packet will not be delivered to the destination. Now protocol, this is the header checksum whether the packet is delivered properly or not. Here it is the source address, means who have sent this packet, through which router this packet is sent, and destination address, next router address, or you can say the delivery address. Here the options plus padding, and this is the data variable, how much data it is carrying, that information is in 32 bits over here. Now the students, this version 4, 4 bits, version bits, this field contains a value in 4 bits which is always, which is 0, 1, 0, 0, see this is the 4, 1, 0, 0 values means 4, this is IP version 4. If it is version 6, so it will be what, 0, 1, 1, 0. So this value is utilized in distinguishing between the IP version 4 and the IP version 6 using 4 bits. Header length, this is of 4 bits. So this value is 4 bits in size and it represents how many 32 bits words are present in the IP header. How many 32 bits words are present. So suppose if 32 bits words means 4 bytes are present, 4, so means 4 4 is 16 bytes will be there. In short, it is also called the header length. So maximum size of the header length is 60 bit only. So here 15, maximum value can be 15. So in the 4 bit maximum value, what you can represent, that is the 0 to 15 value. No? So this value will be given. If suppose, so minimum value will be what? 5, 4 5 are 20. Maximum it can be 15. So its value can be set from 5 to 15. That is the range. So this is you'll study the students in your higher classes in the engineering when you do your computer science engineering or the MCA, that you will study in details. But what I am telling you, this is not in your syllabus, this is only for the information purpose to get the understanding what these packets are, what these packets contains, what are their meanings, why they are used all these bits. So that's only for the idea I am telling you all this. Now next the total length, that is 16 bits. So total length of the IP packet is stored in the bytes. Then what is the total length? It means header length plus a data payload. This value and the header length sums up to the value of the payload. This header length plus payload, how much data. So maximum header is 60 byte and suppose 200 byte payload is there. So this value will be what? 260. So this 260 will be represented in terms of bits. So the maximum number of number you can represent in 16 bits is was 2 to the power 16, which is a large number. Next, flags 3 bits contains control flags of packet fragmentation and reassembly, such as the don't fragment, means don't divide it and do the more fragments. Fragment offset is of 13 bits. After a packet is fragmented and put back together, this field contains the location of it inside the original packet. It represents the number of data bytes ahead of the particular fragment in the specific datagram. Students, next, this is the time to live 8 bits, which I have discussed that how much time over the network this packet will become live, active. After that time, if it doesn't reach to the destination, the packet will be terminated, destroyed. So this field specifies the lifetime of the data packet in the internet system. This field indicates how many hops, means how many routers and packet can make before being terminated. Hops means from one router to the other router. So this also decides that how many hops, how many routers it will pass. So this values goes from 0 to 255. Means maximum 256 hop a packet can do. Maximum. It can be mentioned to be the 100 also, it can be mentioned to 50 also. Protocol 8 bits, the IP version 4 had to specify the type of transport layer protocol, which protocol it is using at its transport layer. TCP, UDP, ICMP. UDP is called the user datagram protocol. This is also called the connectionless protocol. It is very fast. TCP is the connection oriented protocol. It is slow in comparison to the UDP. TCP is indicated by the number 6 and UDP protocol is denoted by number 17 in the protocol bits. Header checksum I have already discussed. This is an error checking layer which is added to identify errors in the header. Students, by comparing this IP header with its checksum, For error detection, it ensures the IP header's integrity, whether there was any tampering, someone has changed the address or not. So this can be identified by the router. Source IP address is of 32 bits. So who have, means this is a sender's address, and destination IP address where this packet to be delivered, that is also 32-bit address. Options a bit, that is a variable, and this field has options and parameters for security purpose, for record route, through which route this router to router it is moving, timestamp, how much time taken to reach to the destinations. So this information in the terms of bits are recorded in the options variable length. So students, next is the framing in the data link layer. So in a computer network and telecommunication, frames are the fundamental units of digital transmission. So at the data link layer, frames are there. A frame consists of a sequence of bits organized into a structured block that conveys the data along with the control link information, such as the addressing and error detection code. So in the data link layer DLL of the OSI model, the framing plays a critical role. So over the network, see, over the network layer we call the packet, over the TCP layer we call the segment, but at the data link layer we call a frame. So framing plays a critical role by dividing the continuous stream of bits into the manageable bits. Suppose the size of the data link layer is going to send this signal to the physical layer, to the wire. So what is the capacity of the wired cable? So according to that, what is the capacity of the receiving window? So if the capacity is low, so what it will do, framing, so it will put the data into a particular frame. That frame you can understand a container just like a mug. So in a mug, how much water you can keep through. So you are taking out the mug of water from a bucket and you are emptying the bucket with the help of the mug. So similarly here also, with the help of the frame, we will empty the entire packets and deliver to the a physical layer, to the cable, transmitting cable, into the manageable and the meaningful chunks which can be carried through that a path. So students, this is a data link layer, this is a network layer. See, above network layer there is a data link layer, below this network layer. Now the frame, how it is happened. So this network layer data will be in the middle, and the data link layer will add its header and trailer. Means information will be there, that again it will contain the addresses and it will pass to the physical layer. So see, data link layer. So it receives, data link layer receives the packet from the network layer, and after that it pass on to the physical layer. So framing is especially important in process such as the time division multiplexing, where data is transmitted in discrete time slots. There is a particular time slot, this frequency of data we will send over this channel. Common data link layer technology like the Ethernet, token ring, frame relay, and the others each define their own specific frame structures. Purpose of framing, why it is thus? Because each having its own capacity, that how much data over this network they can send. So framing gives serves a several purpose in the data link layer. First purpose, what it provides a clear boundary between the frames for the receiver. This means the how much size data at one time it can accept. Includes source and destination addresses, enabling point-to-point communication. Enables error detection and the correction mechanism to ensure the data integrity. It allows the reliable and organized transmission of data. The process of dividing data into frames and reassembling it is transparent to the user and fully managed by this data link layer protocol. So see, what are the types of framing, student? One is called the fixed size framing. Frames have a predefined fixed, which I discussed about. Suppose a mug having a fixed size and fixed volume. No explicit start or end and end delimiters are needed in this. The frame size itself acts as the boundary. Drawback: internal fragments occurs when the data is smaller than the frame size, wasting the bandwidth. So here we do the internal fragmentation also when the data is very small in comparison to the frame size. Means now one mug of water is not available. So in one mug, when you are going to take out from the bucket, so you got only one glass of water is present in the one mug. So that is the internal fragmentation. Padding is used to fill the frame to its full size. If anything space is there in the frame, so we'll do the padding, add some extra information or some other data. So this is in layer, fragment set, flag, header. This is a trailer flag is there. This is the frame data from the upper layer is coming and it is stuffed. The data is pushed here inside the frame, and after it's putting its address and it is passing to the, see, extra 2 bytes address is added here. Now it is passing to the next layer, physical layer. Now frame received, now unstuff, physical layer is doing the unstuffing. Taking out means unpacking, it is doing data to the upper layer. Upper to lower level, variable size frame. This method requires the explicit indicators of frame boundaries and includes two popular techniques. That is the length field. The frame includes the length field that specifies the frame size used in the Ethernet technology. If the Ethernet protocol is used, if the length field gets corrupted, the frame cannot be passed correctly. End delimiter, a unique pattern marks at the end of the frame is given, used in the token ring network. The end delimiter pattern may occur in the data. To solve this problem, two stuffing techniques are used here. Character byte stuffing, used when data is character based. If the data contains a special delimiter character, maybe the $escape sequence is inserted to distinguish it. Example, if end delimiter equals to $, then the data contains $, it becomes $O. Disadvantage, high processing overhead and obsolete in modern systems. Now see, this is the bit stuffing data coming from the upper layer, now stuffed here. Now frames add his header, flag and header and trailer. Now see, some extra 2 bytes is added here. And here again then the unstuffing data to the upper layer. So bit stuffing means end delimiter pattern is a sequence of bits which is separating the data. Whenever this pattern appears in the data, a 0 is inserted to prevent the confusion. Example, problem data, suppose this and end delimiter is 0, 1, 1, 1. After bit stuffing, C1 0 is added at the end. Another example data is this and end delimiter is suppose 1, 0, 0. After bit stuffing, it will become 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. Now problems in framing. What are the problems in this framing, students? So framing in computer network faces several challenges. One is the start and end detection. The receiver must correctly identify the frame boundaries using delimiters or flags. And the synchronization center and receiver must stay aligned on frame timing, especially in the high-speed network. Error handling is a problem. Noise can corrupt the data or delimiters. Error detection methods like CRC or cycle like redundancy check or the checksums are used. Overhead headers and trailers add control information but reduce the usable bandwidth with the help of the headers. The payload will be decreased. Efficiency, the goal is to maximize the payload while minimizing the overhead and processing delays. Compatibility, different devices may use different framing methods causing misinterpretation. Another protocol is the user datagram protocol, which we have discussed. This is also used. This is the connectionless protocol that provides the fast connection and lightweight communication between processes. It does not guarantee the delivery, order, or error checking. It lacks the error checking, making it suitable for real time and time sensitivity. If any packet, UDP packet is lost over a network, it will be not retransmitted by the sender. So this is UDP protocol students basically use in their video streaming, live streaming. Over the voice internet protocol, suppose some packet will be lost, it doesn't affect. You'll get a small glitch, small lag in your video. UDP header. This is the 8 bytes long followed by the data payload. It contains all the essential information needed for transmission. Each port number filled is 16 bits, given a range of 0 to 65,535. This much port means in the computers understand 65,536 ports are available, where port 0 is reserved. So basically only 65,535 ports can be used for sending the data of our receiving the data in a particular computer. So over the motherboards, how many ports are there in a computer? Total 65,536. Port 0 is reserved, which you cannot use, but for the user 65,535 ports are available. So see, this is the visualization of this packet. UDP packets, UDP header 8 byte, UDP data 8 bytes, 16 bytes. Source port 16 bits and destination ports are 16 bits. So this is the 8 bytes UDP header, means 48 bits basically. This is the length, 16 bits, checksum 16 bits. So source port identify the sender port number, destination port length specify the total length of the UDP header and data. Checksum used for the error detection. Where we use these UDP packets, where the low latency is crucial and occasional packets loss is acceptable, where the fast internet you required, fast data transmission you required, in that case you go for the UDP. Where the packet loss is not a major thing, DNS uses this UDP, domain name server uses UDP for fast query response lookup, since domain name queries are small and need quick replies. DSCP uses the dynamic post configuration protocol, uses the UDP to dynamically assign the IP addresses to devices where small control messages are exchanged. VoIP, voice over internet protocol 4G, uses this real-time voice communication UDP. It tolerates some packets loss but not delays. RIP uses the UDP to send the periodic routing updates between the routers. That is the RIP, routing information protocol. NTP and UDP to synchronize the system's clocks across the network with this. So this is all for the today, students. In the next class, we'll continue this topic. Thank you for your kind attention. Jai Hind.